Let me begin. Before I start with the topic for today's lecture, let me make a correction. Yesterday, when I was looking at the Stuckelberg trick, I told you something that is not always true, but it's almost always true. What I said was that the theory, because it has a unitary field like this, will be strongly coupled at a particular energy, at scales above a certain particular energy. This is true provided, I'm sorry, it's true always except in one single case. And the single case is when you have a single gauge boson W, so this big N is 1, and where you don't add any other vector bosons. So L is equal to 1 as well. So you have one gauge boson, you have one, you don't have any additional ones. You have some other fields, that's as many as you want, but you have only one W. So if you have one gauge boson, one vector boson that's going to become a gauge boson, the only group that has n equal to 1, has one generator, is U1. So now you have a U1 gauge theory. In that case, this unitary field is very simple. It's just a complex number. It's e to the I theta. That's how U looks. And if you look at if you calculate this, you evaluate this thing for that particular case, the trace is very simple because everything is a 1-by-1 matrix. So the trace is very simple. There's only one Tn, one generator. Using my conventions that the generators are anti-Hermitian, that generator is just the complex number I. That's it. And so you can evaluate this thing, and you will see it's a very simple expression in terms of the W, the original W, and the exponent of the field U that I call theta. So if you write U equal to e to the I theta, then this curly W will become a linear combination of the original W and this theta in the exponent. And you will see that the ensuing theory is very simple. It's very simple. And so, but that's the only case in which the result of the Stuckelberg trick is that straightforward, that simple. In any other case, that is when big N is greater than 1, and when L or where big N is greater than 1 and all L is greater than 1 as well, then everything I said last time is correct. So there's one exception when there's only one gauge boson and the group that you choose, this G, is U1. Okay, that's the one exception. Do you have nothing better to do? That's actually a nice exercise to follow. Any questions about that? All right, then let me remind you briefly what I did last time. I was trying to find a unified way of doing hierarchy, of specifying hierarchies among the effective operators that will be useful for a variety of applications. And for that, I defined this index that has two expressions this way and that way, and depends on this parameter U, which is an arbitrary parameter. But in practice, I will choose three possibilities for U: U equal to 4, U equal to 2, and U equal to 1. Okay, those are the three cases that I will look at in more detail. And the reason why those are useful, I think, is when U is equal to 4, then the hierarchy that you get is typical of cases where the underlying physics, the new physics, is weakly coupled. U equal to 1 is useful for a particular flavor of SUSY. It's a nonlinear realization of SUSY. I will talk about it in a few minutes, not in detail, but I'll just mention it in a few minutes. And lastly, this is much more important, when U is equal to 2, the hierarchy corresponds to the one used when considering the effective theory approach to low energy QCD. Okay, so that's what. So I'm going to go through these three cases one after the other next. But before I do that, I wonder if there's any questions about what we covered last time. Okay. Of course, you can always interrupt as I go on. Okay. So first case U equal to 4, that corresponds to the standard model of effective theory. In this case, the index is just the dimension of the operator. This is I remind you, little d is the number of derivatives in the operator. Little b is the number of boson fields, or scalar fields for the standard model in the operator. F is the number of fermion field in the operator. And as you know, this is the dimension then of the operator. So S is the dimension minus 4, as noted here. And therefore, the operator will have a factor of lambda to this quantity delta, the mass dimension minus 4, in front of it to make sure that this object together has units of mass to the fourth, and so can be put into the Lagrangian. I omitted putting a coefficient in front of it, since this is just for illustration purposes. And so what I've been arguing is that operators with smaller delta are more important than operators with larger delta, just because the suppression factor is smaller in the first case than in the second. And as you see, since S is really delta minus 4, smaller delta corresponds to smaller S. And indeed, the leading operators have smaller S than the subleading ones. All right, the next case is this one that I mentioned. Will correspond to a flavor of supersymmetry. I think it's the next slide. Yeah, in the next slide, I give you the specific Lagrangian for this case. S is chosen to be such that U is equal to 1, and to assume that all operators have at least one derivative. In this case, the index is just d minus 1, the number of derivatives minus 1. What we will get is that lambda, the general form of the operator, for the case of supersymmetry that I'm looking at, there will be no bosons. So and you'll see this in a minute. So let's assume for a moment theory has no bosons. So you have some fermions, some derivatives, and some suppression factor, like this. And as we will see later on in the course, there will be an additional suppression factor produced by the naturality of the theory that takes this form. Again, the larger the index S, the larger the suppression factor, the less important the operator is. So let me give you the example. Here it is. The reference for this is the book of Wessenberger, Supersymmetry and Supergravity. I forget the chapter number. But they have a chapter on nonlinear realizations of supersymmetry. I'm not going to prove that this is a supersymmetric theory here. It takes me too far afield. But this Lagrangian here, written like it is in fact supersymmetric. But this A is defined in this way. And just a little bit explaining of notation. Sigma A are the sigma matrices. But in this case, they go for little a goes from 0 to 4. The A equal to 0 is just a unit matrix. So sigma 0 is 1, and sigma 1 to 3 are the usual Pauli matrices. This way of writing the Lagrangian relies on the chiral representation of fermions. So with this is a 4x4 matrix. You can take its determinant. It depends in a very nonlinear and complicated way on the fermion fields, and it is supersymmetric. The operators are obtained by doing an expansion in the number of fermion fields, and you find that the coefficient is of this order, provided kappa is of this order. And so what this argument gives is that, the hierarchy produced by this index S here corresponds precisely to the one that is obtained from this Lagrangian, just by naturally, provided kappa, which has units of 1 over mass, has this form. It's again, so it's not a bizarre situation. The last part, so I don't want to go through this in great detail because it's not really, it's an interesting intellectual exercise, but has, as far as I know, no practical applications whatever. What I want to concentrate on most of this lecture is the strongly interacting theories. So strongly interacting theories are difficult because they're strongly interacting. But they're not totally unmanageable. There's things we can say about them, even though we cannot calculate often with the precision that we'd like, or the precision that we obtain in weakly coupled theories. The generic form of operators that we find in strongly coupled theories is this. I mean, there's no mystery. I've attached different scales to the scalars, the fermions, and the derivatives to give as much freedom as possible. As we will see in a minute, these scales are not independent from one another, they're interrelated. I will define then a strongly interacting theory as one where loop corrections are of the same order, no matter how high the number of loops are involved. Now, I will not be evaluating all loops because it's very involved. So I will just be estimating in the following what the contributions are from various loop graphs and then impose this condition and see what I get. That's the thing. So I will choose an operator OA. So OA, it has a number of boson fermions and derivatives, and I will look at radiative corrections to it and require that radiative corrections will all be of the same order. In particular, they will give the same order effects as the tree-level effect, which is just the operator OA. In doing this, I will take the integration momenta to go from 0 to lambda that correspond to the cutoff scale of the derivative. I will assume that each loop gives a loop factor of 16 pi squared that comes from doing the loop integration. And, aside from that, there's not much more to do than kind of estimate what any particular loop will give. All right? So, if you have a loop that has a bunch of, I just realized I changed the notations a little bit. So, think of any loop graph. It has in it a number of vertices that correspond to effective operators. In particular, the vertex has a number of derivatives in it. So because of that, then the number of derivatives will show up as powers of momenta inside the loop integration. Each power of momenta I would simply replace by the worst possible scenario, that is lambda. So if I have a vertex that has dA derivatives, it will produce dA powers of momenta, and it will give a factor of lambda to the dA. So that explains this guy. Each loop integration gives, has a factor of d to the fourth. So I get a 4L factor in the exponent. Each propagator of the, each boson propagator has a power of 1 over p squared that corresponds to 1 over lambda squared. And so I get 2 inverse powers of lambda. And so we have this. And finally, the fermion, any fermion propagator will go as 1 over p and gives me 1 over lambda, and here it is. One thing. Sorry, something got in my eyes. I'm just trying to get it out. Okay. Okay, and so the power of momenta that we get is this kind of thing. Now you might ask, what is this power to minus d? That comes because I'm assuming that the graph gives a correction to the operator at hand that has d external derivatives. And so that corresponds to d powers of the external, little d powers of the external momenta. And so that subtracts from the total, since I have, that subtracts from the total powers of lambda, because in the whole dimensional analysis of the graph, d powers, little d powers, must be accounted for by external momenta. And so they will not show up as powers of lambda, but as powers of the external momenta. And here I'm just calculating the power of lambda that I get. Then there are topological relations that that relate the number of internal boson vertices to the external ones and the number of internal boson lines, and similarly for fermions. And then you find that corrections that you can evaluate, basically it's this factor here at the top, are all of the same order if and only if this is true. So basically what I've done is I've considered a graph that gives a correction to this operator O. Oops, sorry, to this operator O. The graph is composed of vertices. The vertices are also produced by operators of this type that are called O sub A, with B sub A, F sub A, and D sub, little d sub A, and a factor of lambda in front. And the rest is simply estimating the contribution from such a graph by replacing the momenta by factors, by lambda. Each momentum factor is replaced by lambda. And so you get this thing from the graph with this n, and you use these relationships, and you require that this correction that you get is the same as the tree level. That is, the coefficient of the operator that you get is also lambda, little lambda. And when you do that, then this will be true. Of course, this has to be true for any choice of vertices, any choices of dA and of BA and so on, okay, then that will be true only if this is the case. So as promised, for the condition that I used for defining strong interactions, namely this, it can be realized provided the scales involved are related in this fashion and the overall coefficient of the operator is 1 over 16 pi squared. Okay. Let me harp more on this calculation. In doing this this expression, I've taken these coefficients to be the same for all the operators, these little lambdas, and that's what you get in this case. Let me go back and look a little bit more at the possible corrections to the coefficient. And this now, I'm sorry, I changed the notation. This is what replaced the V is for vertex, so that replaces the index A that I've been using here. I am sorry, I just changed the notation. And so if you have a correction to this from an L loop graph, you have a product of vertices multiplied by the loop suppression coefficient, and the condition for strong interaction is that the corrections will be of the same order as the tree level graph.
Yeah, that was the precise question. That till you reach to this point, this method is generic, right? Till you reach to this condition that lambda BF is of the order of delta lambda BF, the methodology that you have used.
It's completely, it's generic. But okay, so yeah, absolutely generic. But notice the twiddle. I didn't put equal. So that means it's just of the same order as that kind of thing. It's not intended to be a precise calculation. So the lambdas are of order 1 over 16 pi squared. Kind of thing. So the correction to lambda will be of the same order because each one gets a 1 over 16 pi squared difference. Okay. So let's see if we can use this to evaluate to evaluate to evaluate the dependence of lambda on the number of boson and fermion fields. That's what I'm looking at now. To do that, imagine that you have a graph. I'm sorry, I keep changing this. Have a graph that has some external lines that correspond to a particular operator, and imagine that you replace inside this graph one operator by one that has two more boson lines fields in it. Then this new guy will provide another correction to the same operators, same guys, kind of thing, where now I've taken these two boson lines and connected one to each other. Just made a tadpole graph of it, addition to it. So this is yet another correction to the operator, but it will be useful for the reason you will see in a minute. You see this this graph here now has two more boson lines inside. Has two more. So instead of being BV here, this guy has BV plus 2 because it has two more bosons. So what I'm telling you is that you have this guy here corresponds to this lambda because now I have two more guys. Times 1 over 16 pi squared is of the same order as this lambda because the only change that I've made is I replaced one vertex by one vertex with two more boson lines. Okay, so I replaced one another, and I made a very simple, of the many possible, one very simple and useful a correction where these two additional boson lines are connected to one another. They're just a type. Because I'm assuming it's strong interacting, the original graph and this new graph will give the same corrections. And that can be true only if the vertex that I had before, from here, compared to the vertex that I have here, provided I include the additional suppression factor from the loop, are of the same order. I put equal, but in reality I mean of the same order. And if this is true, if this is to hold, for any, then the only way of, for this to hold, the only way this can be realized is if the dependence of the number of boson fields is this. I can do exactly the same thing with fermions. I would not go through the exercise, but you will get this thing. So if you combine everything, you get a very precise estimate for the boson and fermion dependence, the number of boson and fermion dependence of the coefficient of lambda, which is precisely this. This is known as the naive dimensional analysis estimate of the strong coupling coefficient. For simple case, simple cases it can be derived, in a case-by-case basis. I decided to do this in the generic case just to show that one can make use of the condition that the theory is strongly interacting as I defined it to extract some information. So now we have an expression of the coefficients dependence on B and F. Now let's put everything together. I have the estimates of these scales that I have here. I have estimates of lambda that depends on B and F. I have an overall 1 over 16 pi squared from another all 1 over 16 pi squared. And I put everything together, and you get this expression for the operator, its coefficient in front. So again, it's not surprising that you get delta. I remind you, delta is the dimension of this thing minus 4. So whatever scale goes in front, it has to have the factor of delta, because only then you will get an object that has dimension of mass to the 4. What is more important here, or more useful, or less direct, is what lambda shows up here, and what, if anything, other factor comes up here in front of it. And from the previous argument, I know I've rushed through this, but I cannot go in full, I cannot do the calculation, just not enough time. I cannot do the calculation in front of you. I'm just trying to describe more or less what I did. You get two things. First, you get one scale that I call lambda phi, a factor of 4 pi to the s, where s is this. Notice that this index s does not depend on the number of boson fields at all. It's independent number of boson fields. So the same coefficient would occur. The same factor, 4 pi to the s, occurs when b is 1 as when b is 10 to the 5. Doesn't matter. It's the same factor. There is a suppression factors of 1 over 4 pi to some power. And the power is determined by the index when u is equal to 2. So this really corresponds, and that's why the index again kind of unifies for different values of this parameter u, various situations. For u is equal to 2, it describes the operators that occur in low energy QCD. I'll make further contact with low energy QCD in a minute. And it gives the suppression factor in front of it. The larger S is, the smaller the effect of the operator, and hence you get a hierarchy. So, the simplest example that I could think of is what are called chiral theories, or chiral QCD, or low energy QCD. And I am going to assume there are no fermions. So in this particular exam simplified version, there are no baryons. The baryons are not there. But there are pions, or more generally, they're mesons. The symmetry of that theory is an SU2 cross SU2 chiral symmetry. This is a global symmetry. This is not the standard model SU2 exactly. It's related in some part of this symmetry is related to it. But this is a left-right symmetry obeyed by the theory. It's a global symmetry, not the SU2 gauge theory of the standard model. The standard model, in the limit where the quark masses are 0, or the corresponding Yukawas are 0, does satisfy this SU2 cross SU2 chiral symmetry. But I'm not going to try to go through that. I'm just going to argue that this is what is observed experimentally. And the simplest way of describing such a situation is using a unitary field again. In this unitary field, the meson fields, the physical meson fields are occur in the exponent, but the Lagrangian that has the invariance takes this form to lowest order, and then it has higher order terms. The point is the following. Each term here, 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 and so on has derivatives, but has various numbers of the field U. Each field U has an infinite number of meson fields. Because when you expand this, you have 1 plus pi squared, pi cubed, plus, and so on, all the way to an arbitrary number. So this and this and this individually have terms that involve 2 pion fields, 3 pion fields, 4, 5, an infinite number of pion fields. So a hierarchy between operators, if it's to be useful at all, should not depend on the number of pion fields. And that corresponds to this situation, in that respect at least, because the hierarchy specified by this index S does not depend on the number of boson fields. And that is why, actually, not why, but that's one point of contact between them. The lowest possible non-trivial term that you can write down that involves this unitary field that satisfies this symmetry is this guy here. The higher order terms, well, they look like this. These are not the only ones. There's more. There's several more. Okay. And what I've been arguing here is that the operators O come from all these guys here. Notice that this scale here, FP, appears here as well. Yeah, let me interrupt myself. Note that this F pi, which has units of mass, appears in front of this here as well, exactly as it is. The reason for that is to have a standard normalization for the kinetic term of the pions, so that the Lagrangian starts with d mu pi, with coefficient 1/2. That's why you have the same guys here. Okay, so think, but you can do the corresponding expansion of this thing. There are no fermions in my theory, so the index is simply the number of derivatives minus 2. So the coefficient you expect to be at most of this order from the previous argument. This is what this gives. And this is what this gives, provided f pi is identified with lambda phi and the coefficients C's are of this order. So for the case here, where we have 2 derivatives, the coefficient here is of order 1, and we only get lambda phi squared. For the next order term, the coefficients correspond to terms with 4 derivatives. So this will go like 1 over 4 pi squared, and so on. And so on. Now, what this does not tell you is how to get all these guys. That is hard. You have to work very hard, make sure that you get all the terms, and make sure that it satisfies the right left-right symmetry. But once you have that, then this argument tells you what order you can expect for these coefficients. Now, the beauty of this whole long argument is that low energy meson physics has been studied for many years, now 60 plus years. So there's an enormous amount of data. There's so much data that we can probe this term and find out the coefficient in front. And we can probe all these terms, the ones that have 4 derivatives. Not yet the ones that have 6 derivatives, but the ones that have 4 derivatives. And the numerical value of these coefficients has been obtained in every single, not for, I mean, there's more than 2, as I mentioned, there's more than 2. There's like 4 or 5, something like that. All those numbers have been obtained. And in all cases, they are of order 1 over 16 pi squared. There's no surprises, no mystery, no nothing. It just works as it justifies the previous argument, at least in this instance, providing an estimate for the coefficients. Okay, so this actually works for this. Now, before I leave this and ask for questions, let me just forewarn you, inevitably, one has to repeat Greek letters. And so pions are usually represented by fields that pi, labeled by pi with an index A. And the number pi is also represented by the Greek letter pi. This pi is not this pi. Okay, this is 3.14159, blah, blah, blah. This is a pion field. And I apologize for any confusion this might produce, but it's a fact of life that sooner or later you will find a confusing notation. This f sub pi refers to the scale associated with the pion fields, not that it's not associated with the pi number kind of thing. So, using naive dimensional analysis arguments, which is based on the statement that a strongly interacting theory will be characterized by having loop corrections be of the same order as tree-level effects, kind of thing. With that, you can get estimate for the coefficients of the operators that describe any type of interactions in such a theory. And what is interesting is that corresponds to the index, that can be, again, corresponds to the index that I've introduced as I said a priori, defining a hierarchy for a particular value of this parameter u. And it thinks it unifies the thing. But so that's kind of an interesting thing and maybe justifies the use of the index. But the really important thing in all this thing is the following. You can use the effective theory to construct operators that, or in this case, perhaps more physical operators that describe the interactions among mesons or among physical particles. And the result is accurate. In the sense, it describes exactly what you see in terms of but a few coefficients. Even though the coefficients cannot be predicted by the theory, they can be estimated. So you have a formalism that tells you what the interactions are and tells you how strong they can possibly be. And in fact, in the cases that we have been able to test it, it works. So this is a proof of usefulness, a practical proof of usefulness of the theory. And so it gives us confidence that the whole approach of the effective Lagrangian that I've been talking to you about is in fact useful in describing nature. It actually is useful. It's not just an intellectual exercise, but it gives you good results that you can actually use. So if you had hoped to have a coefficient that went not like 1 over 16 pi squared here, but you say, for example, what else can it be? It has no units, so it has to be of order 1. You know, people make such arguments. And the answer to that is no, it can be another number, like 1 over 16 pi squared. You know, why not? So just making this hand-wavy statements as to, well, it cannot be anything else because, you know, it has no units, so it has to be of order 1, actually make no sense. Those have to be justified by an argument. Now, let me just make one point, additional point about this thing. If you decide to include baryons, which is perfectly possible, you get an estimate for this coefficient that now depends on the baryon number. And it doesn't look exactly like this. It depends also on the number of fermions in the operator. And the coefficients for some of the fermion operators are much larger. In fact, they are of order 1. There's nothing wrong with that. But the reason that you can trust that is that you made an argument, a coherent, consistent argument that led you to say, well, for that case, these coefficients are of order 1. Okay? You cannot just hand wave yourself into doing that. I keep on saying these things because in my lifetime, there was a strong trend to justify the construction of a collider, the LEP collider, arguing that it would probe physics beyond the standard model immediately, that you would turn the collider on and you would see 50%, 100% deviations from the standard model. That was totally wrong, totally wrong. It was based on assuming, for no reason at all, that the coefficients of the effective operators would be enormously large. A factor of 10, 100, sometimes even 1,000 larger than what they could possibly be. And so, effective theory approach is very nice. It works very well. But if you misuse it, you will get crazy results. And the only person to blame will be you, not the theory. Okay? So it's good. Questions? Yes?
So you have taken the lambda, the radiative correction lambda of the order of delta lambda. So like, is it an assumption or requirement?
Yeah, the idea is it's just the same thing as strong theory. You mean this? This?
Yeah.
Yes. This is the same thing as saying this is the requirement of strongly coupled. That the one loop correction will be just as large as the three level correction. And the two loop will be as large as the two loop correction. It's just that statement. Now, the only thing to remember is the fact that you have sums of terms of the same order of magnitude, it doesn't mean that you will get infinity. Okay? You can, it sounds funny, but 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 doesn't necessarily give you infinity. It could give you something finite because it's not really 1, and because the signs are not necessarily all positive, and because there might be. So you have a general statement about this. I'm just saying something about each radiative correction compared to another. I'm not saying anything about the total sum. So I'm not telling you what the result is of doing an n loop, an infinite loop calculation correction to any particular process. I'm just saying that that my definition of strong interaction is that one radiative correction is as large in order of magnitude as any other. Other questions? Yes.
So, when you talk about the particular example of chiral symmetry,
Yes.
I mean that's being a global symmetry. I mean, what means if you introduce an effective operator which doesn't respect symmetry?
Yes. You can do that. You can do. So the question is, what happens if you decide to purposefully break the symmetry? Okay. So breaking a local symmetry by hand is perfectly acceptable. You break a local symmetry by hand, and you accept the consequences. With this, in fact, you must, as you probably know. The reason why you must break this symmetry follows, as I mentioned, from the standard model. If you assume the quark masses are 0, if the quark masses are not 0, that is, the corresponding Yukawas are not 0, then this symmetry is broken. In fact, it's broken precisely by the quark masses. You say, but you don't have to go and say, oh my God, the end of the world, this is no longer applicable. That's okay. It's okay. You can add to this term. Now you have a different symmetry. So if all the quark masses are the same, instead of having SU2 cross SU2, now you have just SU2. And you can write down then, in that case, terms that have now this reduced symmetry. You keep this because if it satisfies a larger symmetry, it satisfies the reduced symmetry, but you can add more terms that include the reduced symmetry. And those are useful, in fact necessary, as I mentioned, because quarks have non-zero mass. And so you add terms here that describe the quark masses. As it is here, represented here, the quarks that you get, are quark masses because the pions have non-zero mass. As it is here, the pions are massless. There's no mass term for the pions, those whole bunch of terms. But pions do have a mass, and you can add it by including terms that violate this SU2 cross SU2 symmetry. That doesn't violate the recipe of using the effective theory. You have a different symmetry, you can add different operators. Okay? Again, remember part of your process in constructing an effective theory is finding what the low energy particles or the particles of interest are. In this case are the mesons, good. And then you're finding the symmetry of it. And then at the beginning, for simplicity, I've assumed that the symmetry is SU2 cross SU2, which is true if you ignore meson masses. And then you get this. If you have a more realistic situation, as one must do, then you must include meson masses. The symmetry is reduced, and the effective Lagrangian is correspondingly enlarged or altered. In this particular case, the meson masses, the pion masses, are sufficiently low that you can consider them as perturbations. If you kaon masses, they're a little bit too large. Pion masses are 100 MeV, kaon masses are the other 500 MeV. Other heavier mesons, you're out of luck. I mean, these are not a perturbation. This is not a way of doing that. They're just too heavy particles to take this approach. Okay, it's a different approach. Other questions? All right. So let me move on to the next topic. All right. And this is what constitutes a lot of the spaghetti and meatballs, or the dough and rice part of the approach to effective field theories currently. This is what you do if you're working on this thing just about every day. And so I'll go through this a little bit slow. I'll try to give a little bit more detail than in the previous slide because it's just so useful in the current environment. Okay. This situation corresponds to the case where the underlying theory is weakly coupled. The hierarchy, the intrinsic basic hierarchy of the operators, it's their dimension. And so dimension 5 is more important than dimension 6, which is more important than dimension 7. And people have calculated dimension 5, in fact, I'll almost do it on the board for you. People have gotten all dimension 6, 7 also. I hear some brave souls have gotten dimension 8 operators and even dimension 9 operators. I will discuss that. In fact, there's a program that you can use that will give you all the dimensions if you, with sufficient computing power and patience. But I will talk about the need for doing such things as we go along. So, with that, I'm going to look at constructing the effective Lagrangian for the standard model. What I mean by this is I'm going to assume that the standard model is the low energy light theory. And I'm going to construct all this series of operators that embody all the virtual effects of any kind of new weakly coupled decoupling physics, new physics, parameterized by a bunch of coefficients of these operators. Blah, first thing. The second, as I tried to emphasize in previous lectures, the O will be gauge invariant. Gauge here, invariant, refers to the standard model gauge, SU3 cross SU2 cross U1. As I said, the hierarchy is by the canonical dimension. And as I will justify later, there will be one additional thing that's new in this thing, is the following. If you have two operators, O1 and O, that are proportional on shell, what that means is that if you impose the equations of motion, O1 and O give exactly the same effects, except for a proportionality constant, you can drop O1. I will justify that later. This is called the argument that tells you that you can do this, exclude this type of operators. It's called the equivalence theorem, and I'll cover it, as I said, in a little bit. This is useful because when you construct operators of higher and higher dimension, you get more and more and more of them, very many more. I mean, the number grows very, very quickly. And so if you can at least get rid of some of them, not by fiat, but because they are redundant, then at least reduces the number of operators, reduces the number of measurements you have to do to probe the new physics using this approach. And so it simplifies life. So that's why this is useful. Now, the standard model, as I will define it, is the standard model in its simplest form. So the neutrinos have no mass. There's one doublet, and one scalar doublet, and that's it. And, well, and then all the quarks and so on. But you can make it a little bit more complicated. You can imagine an enlarged scalar sector, which is not completely excluded yet. You can imagine adding right-handed neutrinos, because the neutrinos have a mass. And one way of just giving them mass is saying, I'm going to put a right-handed neutrino field and give them very tiny Yukawas. And that's it. Right? You can do that. And then your low energy theory is modified because now you have more fields. You know? Remember, part of the recipe is choosing what your low energy fields are. You have more fields. You have different, actually you have an additional set of operators when you add more scalars. You have an additional set of operators when you add right-handed neutrinos. Okay, so that's something one can do. Before I plunge in, there's a little bit of housekeeping that I'd like to do to make sure we understand one another. And that is basically notation. So as I mentioned, the gauge group will be SU3 cross U2 cross U1. The gauge fields that I will use for those are G, capital G for SU3, capital W for SU2, and B for U1. So these W's, unfortunately, these W's I will also use for the physical W plus W minus field, but I'm sure that they will cause no confusion. If the W has an index capital I, it refers to the SU2 gauge field. Okay. The generators for the GA I call TA, for the SU2 I call tau I. Okay. These are the Pauli matrices. These are the Gelman matrices. The indices. SU2 gauge group labels are capital Latin from the beginning of the alphabet. SU2 gauge labels are Latin from the middle of the alphabet. And I will also have opportunity to use family indices. They're lowercase, these are uppercase. These are lowercase Latin from 3/4 of the alphabet down. Also, we have matter fields The left-handed lepton isodoublet I call L, and these are its representations. The right-handed charged lepton I called E. Now, this is not the electron field, it's just a generic for all three right-handed charged leptons. So the E1 will represent the electron, E sub 2 will, E sub when the family index, so it really has family index, P. So E sub P. E sub P equal to 1 is the electron. E sub P equal to 2 is the muon. E sub P equal to 3 is the tau. And all of them right-handed. Similarly, for the left-handed quark, you have Q, the up-type quark, U, D, and the scalar doublet, phi, the representation. So, and again, U doesn't refer to the first generation. It will refer generically to all up-type right-handed quarks in all three generations, and they will come with a family index. All right. So what I want to do very, very first, oh, it's 11, is what I want to do very, very first is ask if you have any questions about the notation, because I have to stop now. No, okay. So what I will do next time, this afternoon, is explicitly construct the dimension 5 operators in the standard model. I will just go step by step, telling you how it goes. And I hope you'll enjoy that, because I'm not going to do that for dimension 6 or 7. It's much more involved. But I will do that as carefully as I can for dimension 5. But that will be in the afternoon. And my apologies for stepping. But I'm stopping at 11:01. You told me to start at 10:01. So thank you.